Okay, we're going to, like I said, kind of finish up chapter 8 with you guys. That way everybody should be on the same page. So last time we got into, obviously, gases here, and we saw a number of gas laws. So just to remind everybody, some of the relationships that we saw, we first talked about sort of units of pressure, and an atmosphere obviously is a very common unit of pressure. Torr is another common unit, and millimeters of mercury as well. Basically, that 760 number, as we talked about, is really our conversion factor to go from atmospheres to torr or millimeters of mercury. And basically, a millimeter of mercury and a torr is basically sort of a one-to-one relationship between those two. So if you ever need to convert between those two, you just simply change the units. The number stays the same. We also talked about several gas laws that involve really three sort of variables: pressure, volume, and temperature. I believe we started with our good friend Boyle, and that was P1 V1 equals P2 V2. Here, the pressure can be any unit you like as long as they're the same on both sides. And the volume also can be any unit you like as long as they're the same on both sides. This would be at constant temperature. And remember, we also talked about sort of some of these relationships that we see with these laws. And one that we do see with Boyle's law is as the pressure goes up, the volume goes down. And that is because the volume gets much smaller. There's less room for the gas molecules to fly around, causes a lot more collisions, thus causing a lot more pressure in that situation. And opposite is true. If the pressure starts to go down, we usually will see that the volume will go up in that case. Again, in a larger volume, there's a lot more room for everybody to fly around in, which means the number of collisions start to come down, and the pressure also starts to come down as a result of that. We also saw Chuck here. He had a law, Charles' law, that is V1 over T1 is equal to V2 over T2. This would be at constant pressure. This gas law and pretty much every single gas law, when you are dealing with temperature, right, it does need to make sure that it is in Kelvin. So we always want to make sure that you convert the temperature to Kelvin. Again, even if they sort of give you the temperature in Celsius and they want you to give the answer in Celsius, you do have to convert it to Kelvin when you go into the gas law, and then convert it afterwards to do so. The relationship that we see here is the way it's really able to maintain constant pressure is actually the volume actually adjusts to maintain the pressure. So when we increase the temperature, what happens is our gas molecules start flying around a lot faster. And basically, we would expect more collisions to occur and the pressure starting to rise. The way it's able to keep constant pressure is the volume actually goes bigger as well. So we increase the volume in this situation. So even though our gas molecules are moving around a lot faster, they have a lot more room to fly around in. And what that ends up doing is keeping the number of collisions relatively constant. And that's what keeps our pressure from going crazy and keeping our pressure constant. We also have basically the opposite effect there. If we lower the temperature, that usually results in a lowering of the volume. And it's really for the opposite reason. If we lower the temperature, our gas molecules are going to be flying around a lot slower, which would decrease the number of collisions and make the pressure go down. So what ends up happening is the volume decides we'll just squeeze the volume much smaller. And what that ends up doing is allowing the same number of collisions to occur. And that's what keeps the pressure constant. So sort of in the Charles law situation, it is the volume that's sort of adjusting that allows the pressure to remain constant and really allows sort of the same number of collisions to occur. A similar sort of one that we looked at was Guy-Lussac's law. And that is our P1 T1 is equal to P2 T2. This is at constant volume here. And again, here the temperature obviously does need to be in Kelvin. Same situation here, except that our volume will not change in this case. So our volume is fixed, so we don't get that adjustment of the volume. So what ends up happening here is we actually do see the pressure changing in this situation. So as we increase the temperature, because the volume stays fixed, we actually do increase the number of collisions, and we do see the pressure start to increase. And vice versa, if we lower the temperature, we decrease the number of collisions. And again, because the volume is not going to move in this case, it's fixed, we will start to see that pressure coming down. We also then talked about our good friend Avogadro. He had that number. He had a gas law, which is V1 N1 is equal to V2 N2. N is the number of moles, which is what we kind of think about in terms of Avogadro. This is actually under two different sort of conditions. This is constant temperature and pressure. So at constant temperature and pressure, that's sort of where Avogadro's law comes into play. Sort of as the number of moles increases, so is the volume of the gas as well. So they kind of move sort of proportionally to each other. As one goes up, the other goes up, and as the one goes down, the other goes down. Sort of putting together all these gas laws here gives us the ideal gas law. And the ideal gas law is PV is equal to nRT. And out of all the gas laws, this one is a little bit different. First off, there's no like before and after. So there's not like two pressures, no two temperatures. It's basically all just a one situation. The other thing that's important with this gas law is it really is the most restrictive in terms of units, as we talked about. When you're using the ideal gas law, no matter what the situation is, that pressure needs to be in units of atmospheres. The volume needs to be in units of liters if you're using the ideal gas law, and should obviously still be moles, and T does need to be Kelvin. And really the reason why all those guys need to be in those units is what R is. R is the gas constant, and it has a value of 0.08206. And it has units of liters times atmosphere divided by Kelvin times mole. So the good news is you're probably usually going to be given R, and they would have those units. So if you ever are not sure what units should go into the ideal gas law, you could kind of just look at the units associated with R, and you'll know what it is. Again, a lot of books and people will use more of a rounded number for this guy, like 0.0821, and that's perfectly fine. I personally use kind of the other number most of the time. Also, another note on R is in a lot of gas problems, they don't tell you about R. They don't say, hey, you have R, or R is this. It's just sort of a number that you should always think of. You always have, and it's just kind of assumed that you know what the number is. But it's very, very rarely in an actual problem, they'll tell you, hey, the value of R is this or anything like that. So sometimes people miss it that way or don't think about it, but always think about that you do have that number. There are also a couple of final relationships that we also talked about. One was STP, and that stands for standard temperature and pressure. And it basically is giving you two values. So for pressure, that is 1 atmosphere. And for temperature, that is 273 Kelvin. So in a problem, if it says under STP conditions, those are basically what you would use for temperature and pressure. The temperature would be 273. And again, the pressure there would be 1 atmosphere. Now, there is a certain relationship that is sometimes helpful if you are at STP conditions. So at STP conditions and only at STP conditions, 1 mole of a gas will equal 22.414 liters. This is a conversion, again, I'll circle it. You can only use if it is STP conditions. So it does need to be obviously the temperature 273, does need to be the pressure of 1 atmosphere. If it's not one of those two things, or those two things are not there, then you cannot use that conversion. The reason you might want to use that conversion factor is if you are under STP conditions, it could help you not have to use the ideal gas law. So you could kind of skip using the ideal gas law and kind of use that conversion. The good news is if you're unsure if you should use that conversion, or you can't remember that conversion or whatever, you could always use the ideal gas law. So you could always use the ideal gas law no matter if it's STP conditions, not STP conditions. If it's STP conditions, you put into the ideal gas law, the pressure is 1 atmosphere and the temperature is 273. So you know, if you're not sure, just default back to this guy, and on those situations, then you could kind of just put the numbers in. Any questions on any of that stuff we talked about last time? Yeah. Yeah. Yeah, P is equal to 1 atmosphere, which again, sometimes people will sometimes use it, you know, as like 760 torr, 760 millimeters mercury, because that does equal 1 atmosphere. The technical usually definition is 1 atmosphere, but you could use its equivalent in other units if it's okay in that gas law. Yeah. So for example, if you were doing something like, say, Boyle's law, and you wanted to do it at STP, you could use 1 atmosphere, or you could use the 760 millimeters mercury or 760 torr, and it would all come out the same as long as the other side was also using millimeters of mercury or torr. Other questions? Okay, so then let us continue on here. So we can look at sort of changes in all three of those variables: pressure, volume, and temperature. And if we sort of take the ideal gas law and solve it for R, which is a constant, we do end up with this law right here, which is sometimes referred to as the combined gas law, as it kind of takes everybody into account. And this is P1 V1 over T1 is equal to P2 V2 over T2. Here, these are our same sort of guys that we've seen before. So the pressure can be any unit as long as they are the same on both sides. The volume can be any unit of volume you want, again, as long as they are both on the same side, opposite sides the same. But just like everything else, you definitely need Kelvin there for your temperature. This again is maybe the one that gives people the hardest time rearranging. So a reminder, as we talked about, that, you know, if you are going to move something across the equal sign, they do end up in the opposite location. So if you think about sort of top and bottom, anything that was on the top left, if you go across, will end up on the bottom right. Anything on the bottom left, if you go across, will end up on the top right, and vice versa. If you're on the top right and you need to move it across, it ends up on the bottom. And again, that's sort of a quick way you can rearrange it. An equation, which again, we're basically solving by multiplying and dividing, is essentially what we're doing there. But if you just want to quickly rearrange it, just put it in the opposite location when you go across the equal sign, and you'll probably rearrange it correctly. Any questions on that there? All right, so why don't we try one here and see how our rearranging skills work. Consider a sample of oxygen at 27 degrees Celsius with a volume of 9.55 liters and a pressure of 2.97 atmospheres. Pressure is changed to 8.25 and heated to 125. What is the new volume of the gas? So take a couple minutes, see what you come up with. Okay, let's take a look. So remember that when you're working gas law problems, you know, there's a number of sort of gas laws to choose from. You know, the best piece of advice is really just to pull out the information from the problem, sort of label them as pressure, volumes, or temperatures. And a lot of times, just by looking at it, it could kind of point you in the right direction. So if we kind of take that approach, we obviously have a temperature here that is 27 degrees Celsius. We have a volume that is 9.55 liters. And we obviously have a pressure that is 2.97 atmospheres. We have another pressure here that is 8.25. And we have a temperature that goes to 125 degrees Celsius, and we are looking for a volume. So just by writing it out there, you know, it should really sort of resemble, obviously, the combined gas law that we just talked about. Clearly, none of the other sort of formulas would work, right? There's no other ones that really has all three of those variables together. So we definitely would want to use P1 V1 over T1, P2 V2 over T2. We could even check off everything. You know, we could call all the first sort of values the ones, the second ones the twos. And if we check off everything, really the only thing we don't have is V2. So we do want to rearrange it. And again, if you just want to sort of do it quickly, we see T2, we need to move to the other side, which means it's going to end up on top. We have P2 that needs to go to the other side, which is going to end up basically at the bottom there. And if we do that, we will end up with P1 V1 T2 divided by T1 and P2 would equal our V2. So again, just sort of by switching locations there, we'll get everybody into the right spot. Also important to make sure you understand what temperature goes where, for example, what volume goes where. It's very common people will sort of reverse the numbers and stuff like that when they put them in. So now that we got everybody, we do want to make sure a couple things. Our pressure units are both the same, so that's good. Again, if one of them were different, we would need to convert it to the same units. In this case, our temperature, we do need to convert to Kelvin like every other gas law. So that's going to give us 398 Kelvin when we add 273. We're going to add 273 to this guy, and that's going to give us 300 Kelvin. And at this point, we have everybody in the right units. So P1 here is 2.97 atmospheres. V1 is 9.55 liters. And T2 is what goes up on top, which would be 398 Kelvin, all divided here by T1, which is 300 Kelvin, and P2, which is 8.25 atmospheres. In terms of units, the atmospheres on top and bottom will cancel. The Kelvin up on top and the Kelvin on the bottom will also cancel. That will leave us just one unit left, which is liters, and that's good because we are looking for a volume. So that all works out really well. That means we take 2.97 times a 9.55 times a 398 and hit equals. We divide by 300, hit equals, and divide by 8.25 and hit equals. And we're going to end up with here, we'll call it a 4.6 liters at that point. Any question on that calculation there? So again, I would say this one out of probably all of them, because there's 3 different variables on each side, people very commonly rearrange it incorrectly. So if it is problematic for you, maybe you should take some time, obviously, and make sure you know how to properly kind of move everybody around. And again, just simply opposite locations is a really kind of convenient way of doing that. Yeah. Yeah. So let's see here. That's a good question. Really, yeah, I used it to really base off of the 27, because when I converted here was 300 even. And I really didn't put the decimal point there, which really meant this one significant figure. So it really had 2 sig figs. So 2 or 3 would have been okay, acceptable here. 4.56, I think, was maybe what you got there. And that would have been okay. And probably looking at it, maybe should have been 3 sig figs as well. So that probably would have been a little appropriate there, as everybody else is pretty much 3 sig figs. Other questions? Okay, the next thing we're going to talk about is something that people sometimes get a little nervous on, which is Dalton's law of partial pressures. It sounds very scary and a big name. But it really just deals with sort of mixture of gases. So very often gases actually do come as sort of mixtures of different gases together in the same container. So when we sort of look at a situation like that, I just kind of draw it here, I think. We'll go here. So if we just had a container here, and again, we just had perhaps just one gas molecule basically flying around, all the pressure that would be associated with this particular container would only come really from one gas, which is the only gas that's in there. And that means in this case, the total pressure would be a result really of all the pressure that's coming from gas A as it's flying around. Now, if we took another container, gas B, why don't we go with D, why not? In this case, we have a lot more different gases that are flying around. They are each causing collisions and with the walls of the container, and thus causing pressure. So no longer when we think about sort of the total pressure here, is it really just a result of one gas molecule that's flying around? It's actually a result of all the gas molecules that are flying around. So it is a result really of the pressure associated with the A molecules that are flying around. it is the pressure associated with the B guys that are flying around. And since I skipped the alphabet there and went to D, it is the pressure there of our D gas molecules that are flying around. So what these are referred to oftentimes are partial pressures. And they're referred to as partial pressures. So that would be like the partial pressure of A, the next guy would be the partial pressure of B, and the last guy would be the partial pressure of D. They're referred to partial pressures because they each contribute basically to the overall total pressure that we see in a particular mixture. So each of them are partially contributing to them, which is why they're referred to as partial pressures. The total pressure here in a situation would be like if you took the barometer reading in the laboratory, the atmospheric pressure would be really the total pressure that we would see here. Now, how do we actually get the partial pressures? But if we think about sort of what is happening in this container, we basically will get the partial pressures by one way is to simply just use the ideal gas law, which is PV equals nRT. And here we would solve for P, which would be nRT divided by V. And one thing that makes something sort of an ideal gas is the idea that it can basically be in a container with other gas molecules, and pretty much they will not interact with one another. So that's sort of an ideal situation that even though we have multiple gas molecules flying around in the same container, it's almost like they're in there by themselves because they really don't interact with one another as they're flying around. And the good news on that is we basically could just do three, for example, in this problem here, we could do just three separate calculations using the ideal gas law, one for each gas. So we could do this for, gas molecule A, we could do it for gas molecule B and gas molecule C or D in this particular case. Now, a couple of things which are good is because all those gas molecules are basically in the same container, the volume for all those gas molecules are really going to be the same because they're all basically in the same container. And the odds are that container is sitting in the exact same room, which means that the temperature pretty much for all the gas molecules will be the same. And R, which is a constant, will also be obviously the same for everybody that's in that mixture. So what it usually boils down to when you're doing sort of an ideal gas law in a partial pressure situation is most of the time, you just need to figure out how many moles of each gas you got in there. And then you basically go into the ideal gas law individually 3 times in this particular example. And then all you would do is simply add up each of the individual partial pressures, and that would give you your total pressure. So that is a very common way that we sort of solve partial pressure problems, which is simply just use our ideal gas law, basically do individual calculations for each gas separately. Again, assuming ideal situation where they're not interacting with one another, and then we get all the partial pressures, and then we simply just add them together, and that will give us our total pressure. Any questions on that? Now, since we're using the ideal gas law here, just like we were talking about earlier, you do need to make sure that everybody's in the correct units when you go into the ideal gas law. So again, things need to be in atmospheres, liters for volume. Obviously, temperature needs to be Kelvin, so those type of things you got to make sure of. Any questions on that? So why don't we try one here? A 5-gram sample of helium and a 5-gram sample of neon are put into a 2.5 liter container at 27 degrees. Calculate the partial pressures of each gas and also the total pressure here. So helium on the periodic table is 4.003 and neon is 2018, we'll call it. So you're actually looking for 3 answers here: the partial pressure of helium, the partial pressure of neon, and then what is the total pressure of both of those things together. So again, you basically have a container that has helium and neon in there, and they are both flying around contributing to the pressure. So take a few minutes here and see what you come up with. So this is obviously a mixture of gases. And again, if you weren't sure, you could again pull out the information. We do obviously have a volume that is 2.5 liters. We got a temperature that is 27 degrees Celsius. We are looking for a pressure, and we are given grams, which is not really helpful in gas laws, but we do know we could go from grams to moles. which basically means we have N as well. So we got P, we got a V, we got an N and a T. So again, that should put you towards the ideal gas law. And that's really what we'd want to use here. We would want to use PV equals nRT. Here we would want to, as we just talked about, basically solve for P for each of the gases individually here. We do need to do a couple of conversions. Obviously, we do need to take our temperature here and convert it to Kelvin. So if we add a 273, that is going to give us 300 Kelvin in this case. We also want to take probably both of our grams there and convert them to moles, so we have them in moles. So that's what I'm going to do first. We're going to use the molar mass to convert our grams into moles. So 5 grams of helium dividing by the molar mass from the periodic table, 4.003 grams per mole, gives us call it 1.25 moles of helium. We'll do the same thing here for neon. So dividing by 2018 grams per mole will give us for neon 0.248 moles. So we basically now have the moles. We converted our temperature into Kelvin. Our volume is okay for the ideal gas law because it's in liters. So we're good on that. So basically, we're just going to do 2 separate calculations, one for helium and one for neon. So we'll start with helium. The partial pressure of helium would be nRT divided by V. We want to use the moles, obviously, for helium, which would be 1.25 moles. Remember that R you always have, so it's a constant, 0.08206 liters atmosphere Kelvin mole. Our temperature that we converted to 300 Kelvin, all going to be divided by our volume, which was in liters, 2.5 liters. Again, the moles will cancel, the Kelvin will cancel, the liters will cancel, leaving us just atmospheres that are left over, which again is good because we are looking for a pressure. We're going to take if we turn our calculator on, 1.25 times 0.08206 times 300 here. We're then going to divide by 2.5, and we will go with 12.3 atmospheres. This number here would represent the partial pressure of helium. Partial pressure of helium in this case. Any question on that calculation there? We're pretty much going to do the identical calculation for neon. And again, because they're in the same container, volume's the same, temperature's the same. Really, the only difference here is we want to make sure we use the moles for neon in this case. So the partial pressure of neon would be using the moles for neon, which is 0.248. Our gas constant, which is still the same number. Our temperature, which is the same because they're in the same container, all divided by our volume, which is also the same because they're in the same container. That gives us liters canceled again, moles canceled, and Kelvin canceled. Once again, leaving us atmospheres, and 0.248 times 0.08206 times the 300 and divided by 2.5, going to get us a 2.44 atmospheres. This would represent the partial pressure of neon in this case. Any question on those 2 calculations? Really just an ideal gas law, right, for each of them separately? How do I get the total pressure at this point? At this point, we can simply just add up each of the partial pressures, and that will give us our total pressure. So our total pressure would be 12.3 plus 2.44, 14.7 atmospheres. Any question on any of that calculation there? Yeah. You do. You are responsible for them. I think one or two might be provided, like the ideal gas law. I think whatever it says on the review sheet. So I know ours obviously will be provided for you, and I think maybe you have the ideal gas law, whatever it says on that review sheet. But the other ones you should sort of know. Okay. Other questions? So why is helium contributing most of the pressure in this mixture? It obviously is right at 12.3 versus 2.4. Any ideas why it is actually causing more pressure than the other gas? It actually has to do with the molar mass. Helium is only about 4 grams. Neon is 20 grams. Because helium is actually a much lighter gas, it actually moves a lot faster, has a very higher velocity, which means because it's flying around a lot faster, it's going to be in more collisions. And because it's in more collisions, it's actually contributing to more of the pressure in this mixture than neon, which is a little heavier and flying around a little bit slower, not causing as many collisions. Other questions on that? Okay. So that is a common way that we do partial pressures. Another sort of partial pressure situation that we sometimes come across is pretty much like what you did in that lab, I think. So you take something like potassium chlorate here and some manganese dioxide, which is actually a catalyst. And if you did that experiment and you didn't add enough MnO2, it was probably a very long night for you, yes, because nothing happened. They really should tell you dump a whole bunch of that stuff in there so you could go home. But that actually is a catalyst, which will speed up the reaction. About halfway through or more, the lab instructor goes, all right, start dumping some of that stuff in. I want to go home tonight. No, that's usually what I say at the beginning. When you do that, obviously we get actually a decomposition reaction that occurs in this guy, as you might remember, and it will basically decompose into KCl. And the gas that we actually get is oxygen gas that actually gets developed. So obviously the test tube is closed, so the oxygen gas has really nowhere to go but kind of down here and through this tube into usually a container where you have a lot of water in there. And as the gas comes in, it basically displaces the water, right? The water kind of bubbles out, the gas kind of goes in there. And what you end up with is usually a section here in that collection container that appears to you to be empty, but it really is not empty. It's actually where your gas ended up. And that is where, in this particular example, the O2 gas, the oxygen gas ended up. Sort of a consequence of doing an experiment like this where water sort of involved is a lot of times the reaction will generate heat. And when heat and water are together, basically water will start to evaporate and it basically will create water in the gas phase. So in addition to like the gas you're interested in, which is the oxygen in this experiment, you will also collect some water vapor, is referred to, as sort of another byproduct of really not the reaction you're looking at, but how you actually collect the gas in this particular case. So in a lot of cases, we're not usually ever interested in really the pressure associated with the water. And a lot of times what we really are looking for is just the pressure of the gas that we collected. So what we end up in a situation like this is that the total pressure is equal to the pressure of the gas you're interested in, like oxygen in this case, plus the vapor pressure of water. And the vapor pressure of water is usually a value that you could kind of look up at a table based on temperature and stuff like that. So typically we actually end up doing almost, you could think of it like a correction calculation where the pressure of the gas you're actually interested in, you take the total pressure and you subtract the vapor pressure of water. So it's almost like a correction value or calculation that you do, sometimes referred to as getting the pressure of the dry gas. You kind of subtract off the water component to it. So this is, again, another very common situation whenever you collect a gas over water, sometimes referred to or saturated with water vapor. It's usually this situation, and usually somewhere along the way in your calculation, you got to kind of do that calculation there where you subtract off the vapor pressure of water from the total pressure. Where would the total pressure come from? If you were in the laboratory, it would come from the barometer reading of the room. If you were in the book problem, they would just tell you what the total pressure probably is in the actual problem. So let's take a look at one like that. what we see here is the sample of oxygen gas is saturated with water vapor at 30 degrees Celsius. And that is the key to know that we're dealing with this situation is those words saturated with water vapor, collected over water is another way it's commonly referred to. The total pressure is 753 torr. The vapor pressure of water at 30 degrees is 31.824 torr. What is the partial pressure of oxygen? So in this case, the total pressure, like we were talking about, would be the pressure of oxygen, which we're interested in, plus the vapor pressure of water. In the problem, they gave us the total pressure and what we would normally find on a table. They also gave it to us in this problem as well. So we could rearrange this and solve for the partial pressure of oxygen would be the total pressure. And we would take this and subtract it to the other side minus the vapor pressure of water. That would give us, since they're nice enough to give us the values here, 753 minus 31.824 torr. Again, this number most likely is usually found like on a table, or you look it up on a table. And if you do that there, we do end up with 753 minus 31.824 gives us roughly 721 torr. And they do want it in atmospheres. So to convert it to atmospheres, this is where we would use our 760 number. So 721 torr divided by 760 torr is an atmosphere. So dividing by 760 gives us a pressure of the dry gas 0.949 atmospheres. So this is again a common sort of partial pressure situation, also a very common laboratory correction that you do a lot because a lot of times it's conveniently to collect the gas with water. And again, the key words to look for in that sort of a book problem is something mentioning water. So again, saturated with water vapor, collected over water, something involving water usually will mean you need to do some type of correction sort of calculation like what we see here. Any questions on that there? So just to finish up here, these are some of the parts of the kinetic molecular theory of gases. And a lot of these things we sort of talked about a little bit. But gases basically consist of tiny particles. They're either atoms or molecules. These tiny particles are so small compared to the distances between them that the volume of the actual gas molecule is thought to be basically negligible or zero. So if you think about a lot of gas law problems, they oftentimes talk about the volume of the container the gas is in rather than the volume itself. And actually, number two here is really what makes something an ideal gas. Under ideal conditions, it's really the volume of the container that's more important than the actual volume of the gas molecule. Is really small comparison to that. Particles are in constant motion. And again, it's those collisions with the container that causes the pressure we associate with it. The number four here is really the second thing that makes something an ideal gas, which is the particles are assumed basically not to be attracted to one another or repelled by one another. And that's really why when we were talking about partial pressures a second ago, even though there were three different gases in there, we could do each gas like they were in there by themselves. And that's the idea. They're not interacting with each other, which means they really have no effect on the pressure of one another because there's really no interaction that occurs. Obviously, the average kinetic energy of gas molecules is related to the temperature. So obviously, as the temperature increases, we do expect the gas molecules to fly around faster. And as they kind of slow down, they will obviously move slower at a lower temperature. And then again, just some of our relationships here that we talked about, which is, again, at high temperatures, moving faster, more collisions, lower temperatures, less collisions. Again, in a container where the volume does not adjust, we will see that pressure increase or decrease depending on whether the temperature is increased or decreased. And obviously, the way we are able to keep constant pressure, like we talked about with Charles' law, if we have a volume that's able to adjust, by adjusting the volume, it keeps the collisions relatively constant and the pressure relatively constant as well. Any questions on any of that stuff there? So one last thing was sort of a question a second ago about sort of the formulas and stuff like that. When we were looking at P1, V1, T1 is equal to P2, V2, T2. This combined gas law is a great one to know because it really can give you like Boyle's law, Charles' law, and all those other laws. And if you remember this one, and pretty much if you know what's being held constant or what is not given to you. So if you have a problem where you're not given anything about temperature, or you're not given, or it tells you temperature is constant, you essentially just take off the temperature part and then you have Boyle's law. If you have a problem where you see that the pressure is being held constant, you just scratch out the pressure on both sides and now you have Charles' law. If you have one obviously where the volume is being constant, you scratch out those guys and now you have Guy-Lussac's law. So if you remember the combined gas law and basically just take out whatever part is not given to you or is held constant, it was an easy way to get back to kind of those other gas laws. So it's a good way to sort of remember it. Any questions on gases there? All right, you guys should then be caught up.